Hi, today I'm going to show off my new and improved, well not necessarily new, but certainly improved Rotary Tactile Stimulator. Last time we saw this, we were having issues with the lower speeds and at 0.3 and 0.6 centimeters a second linear being terrible and steppy. It had a pretty poor resolution. Since then, we've improved this significantly, as you can see here. What we've done is change the servo control mechanism completely. Also, we've put a gearbox, a 2-to-1 ratio approximately. It's close to 3-to-1 actually, which means that the servo has an output of 180 degrees, maps to about 60 degrees on the actual arm output. We've also added, and this is pretty much going to be the final design. Lego is, pretty good stuff. We've also added a clutch. That means that when a participant's arm actually gets hit by the mounted arm, it doesn't push through their skin and doesn't risk anything, which in this case, this is a very powerful servo motor, and going through a 3-to-1 ratio means it's 3 times more powerful. So it's really a genuine risk that you could hurt yourself using this. I've designed this to have a small margin between the brush connection and your arm, but that doesn't account for people having larger arms and the progression of your arm size over the length of the sweep. As we showed last time, this is being controlled through an Arduino and a potentiometer, but unlike last time, we also got this running off a battery. This is a standard sort of setup for anything that doesn't have access to AC power. In this case, we had to run the Arduino off a USB port to get the 5 volts, and the servo off a 5 volt AC wall wart, which was less than ideal. In this case, we've now only require one connection, which we've got 2 battery eliminator circuits at 5 volts and 12 volts. The quick discussion about how this works is here. So we require obviously a rotary tactile stimulator, and it has linear speeds between 0.3 centimeters a second to 30 centimeters a second. That's 100 times difference in linear speed. So what we've got, and this matching to our design, we've got an arm of length 25 centimeters with this brush here of about 4 centimeters. A participant's arm will be down the bottom here in some kind of fashion like so. The swept distance, whilst not really a big deal, is the whole perimeter is 0.19 meters. So we can calculate the RPM of our motor. As such, the RPM of the motor is between 0.72 RPM and 72 RPM, which is a really big difference, which is somewhat hard to control. So what we've implemented now is, because we only need a small sweep, sort of getting lost here, there's not too much I really can talk about, but because there's a small sweep, there's a small range of motion, we can use a servo, and it is possible to get a good speed, control from it. Our servo is spec'd out for using a 60-degree sweep of 0.14 seconds to 13.89 seconds. And this sort of gets into the control aspect, where we have a 1,800 steps between 0 and 180 degrees. what we now have is, because we have a 2-to-1 ratio, or a 3-to-1 ratio, let's just say it's 2-to-1, we have a positioning accuracy of 20 steps per degree, which would have originally been 10 steps per degree. And the really important thing to look at here is the steps per second, because this is what you physically feel. So at a really slow speed, you feel about 50 steps per second. At a high speed, those steps are nearly imperceptible. So the perception of those stepping, I'm not exactly sure of, but we'll show in a moment just that speed. Also, in the previous design where we did see visible stepping at the lower speed, that was a 1 step to 1 degree ratio. So in this case, this is 20 times more, or it has a resolution of 20 times greater steps per degree. So now we're going to have a look at the control. The control has not varied since the last time we had a look at this. It takes input through a potentiometer, and its output obviously through the arm here. So at the moment we're running at the slowest speed, and this will mean that it's about 13 seconds per sweep, maybe? I can't remember. It's quite a long time. I think it ends up being about 43 seconds. That really sounds very professional, doesn't it? If I put it on table so we're not moving so much, you can see it moves slowly, and this stepping is fairly imperceptible. What I'll do now is I'll reset the system. I'll go to our fastest speed and I'll reset the system, so then we can show the fastest speed. So that's our fastest speed, which is approximately 4,300 steps per second. It also, we've programmed it to do a series of sweeps for up to 10 seconds. This doesn't mean it stops sweeping at 10 seconds, it just means after 10 seconds has elapsed, don't perform any more sweeps. So at our slowest speed, it takes 23 seconds to go one way, but it hasn't gone through a whole cycle, so we go back to the start. In this fastest speed, it takes about 9 seconds to do approximately 7 cycles, and so it returns to the start, which means it's about 13 seconds, say, and it doesn't perform any more sweeps. In a final design, we'll have markers that show the speeds, how it matches to this potentiometer. But it should be fairly explanatory, although it's a bit difficult to get the right speeds. I can't determine what this is, but I know it's about the second speed because I've added an indicator on the Arduino that shows what speed it may be at. By just an on-off indicator means it could be one of 3 options. The final thing to note in the system, as you may have heard, is that it is fairly loud. We've put it on a foam block, so there's this, the vibration of the motor doesn't become amplified through resonance, say, of the desk. If we do put it down, we can illustrate how loud it is. And also, the benefit of having this clutch here, by the way, is you can readjust the position. So you can hear it's much louder. And if we set it to our fastest speed, you'll also, see that it's much louder as well. Maybe not see, but definitely hear the difference. I'll reset it so we can do it quicker. Yep. There we go. just unplugging it, it all turns off. It's fairly simple. And that's a Rotary Tactile Stimulator. Yes, it's made out of some yellow Lego and green Lego, and it's not very color coordinated, but it works fairly well, I think. I couldn't imagine any more improvements that's possible. Yeah, you cannot get any better servos because mostly they have that resolution. The next step you'd have to go is to a DC motor with an encoder. Doing that would introduce many times more complexity than is really needed. Also, the cost is probably more, but given I haven't really done much research into it, although I'm very aware of what's required, I can't quite say that it really is more expensive. Anyway, there we go. It's a pleasure. Have a good afternoon.